I will present today the results of a study that I did with my colleagues from the Moscow State University as well as from Boston College. A study that was comprised of an intervention training session or set of sessions aimed to improve numerical magnitude and understanding in kindergarten students. I want to start with a point that I tried to make this morning when I was asked the following question. I was asked, what recent advances in cognitive science do you think are particularly interesting for math education right now? And I decided that to me, the most interesting advance has to do with a whole series of studies that focused on investigating the link and uncovering the multiple links between spatial reasoning and mathematical problem solving. Mostly at the moment, it's correlational findings showing, for example, that children who achieve at high levels in mathematics appear to rely a lot on their spatial visualization skills, and so on. So the present study is sort of a follow-up on this accumulating body of correlational research, the one where we designed an experimental investigation looking into a causal relation between spatial and numerical thinking. And the aspect of spatial mathematics that we have focused on is measurement, whereas the aspect of numerical math domain that is a particular focus of this research is children's understanding of numerical magnitude knowledge. What attracted us to this particular pair of domains is the fact that even though they're often viewed as very distinct areas of mathematics, in fact, they share some key conceptual elements, as I will try to illustrate in the next couple of slides. The first important concept that is really foundational both for the understanding of measurement and for the understanding of number is this idea about equal intervals between numbers, whether we think about a mental number line or about a ruler. So in order to be able to carry out a full range of math operations in the future, it's critical to know that the numerical distance between, say, 5 and 6 is the same as between 95 and 96. And yet for young children in kindergarten and in first grade, this idea is not super intuitive. In fact, they have difficulty with it and tend to overestimate distances between 5 and 6, perceiving them as, smaller numbers, perceiving them as bigger differences than those between bigger numbers. The idea about equal intervals between numbers indeed is quite abstract and perhaps not intuitive, requires some time, a lot of accumulating experience dealing with numerically relevant stimuli in order to extract that idea from this experience. In measurement, where the idea of equal intervals essentially is equivalent to the idea of unit of measurement, that same concept could be potentially transmitted to children, taught to children in a somewhat easier way. We hypothesize that it is easier to understand the nature of the unit of measurement when you do it through concrete measurement experiences where spatial clues, spatial cues are available about the extent that can highlight the particular sort of measurement principles, particular features of the relation between individual units and overall magnitudes. Another such foundational idea that is shared between the two domains is the idea of relative magnitude, or the relation between magnitude and unit size. So the mature understanding of numeric magnitude implies that value of a number is proportional to the size of a unit interval. So the numeric value 5 may refer to 5 single units, or 5 tens and 5 hundreds. And in all those cases, it refers to very different magnitudes. It could be even 5 tenths fraction. But still, we're talking about the same symbol, 5, referring to very different numerical magnitudes. Another idea that is not superintuitive in the domain of number reasoning, and yet potentially could be conveyed through the affordances of measurement activities more clearly to young children. And so this sort of logical analysis shows that there is a substantial conceptual overlap between numerical and magnitude understanding and measurement, and the challenges of understanding some concepts in the number domain correspond to some actual affordances in the measurement domain in terms of understanding similar or parallel concepts, which led us to a hypothesis that if we design a measurement instruction focusing on conceptual understanding of unit, it may promote numerical magnitude understanding. And so that's the essence of this present research study. It's an intervention that directly targets understanding of measurement and indirectly asks this question of whether such intervention may advance numerical magnitude knowledge. The study was conducted here in Russia with kindergarten students. The participants in our study all followed the same curriculum, and so we were curious as to what their measurement knowledge was at the time of our intervention. We found out through interviews with teachers that children were introduced to a ruler, and they had a single activity where they measured objects with a ruler using standard procedure. So there wasn't much, if any, instruction focusing on the conceptual understanding of units. It was essentially confined to learning of a standard procedure. Our study followed a standard sort of intervention design where the intervention was preceded and followed by a post-test. The intervention included 8 training sessions in small groups of children. Within each classroom, we assigned children to either experimental or control condition. In the control condition, children spent the same amount of time with the instructor, the same amount of additional time, I mean. And they essentially received additional practice with the same types of topics that are covered in their regular math instruction, what's often referred to as business as usual control condition. In the experimental group, children spent all this time just on measurement activities. And in the design of our activities, we were guided by several considerations. First of all, in terms of content, we identify certain conceptual principles of measurements that are relevant to numerical magnitude knowledge, and for each of these concepts, we wanted to design a series of activities. In terms of instructional approach, we wanted in particular to emphasize spatial cues that are available in the process of measurement as a means of understanding quantity and magnitude. We began instructional sessions with a particular focus on concrete spatial representation. So children were using little strips of paper that represented units of measurement, and at first, they used the strips of the same size. Then we introduced units of different size. Following this the use of concrete representations, we utilized gestures as sort of an intermediate stage between concrete representations and internalized representations, where the instructor demonstrated, this type of gesture to refer to a unit, or a bigger, to refer to a bigger interval. Another kind of gesture to convey this idea of unit of measurement as an interval of length, in the case of linear measurement, that corresponds to magnitude. And then children were encouraged to engage in spatial visualization of relations between units and magnitudes. I have, because of the limits of time, I have just one sort of illustration of the various types of activities that were included in this intervention. As you can see here, there are 3 rulers, and in our activities, sometimes we use traditional rulers, sometimes rulers like this that did not look like traditional ones. So children were shown 3 rulers with different unit sizes with different units of measurement. And having been presented with these rulers, they were then presented with first an object and a picture of an object. So let's imagine they were presented with a pencil, and they were told that this pencil was measured with one of the rulers, and it was determined that it was 2 units long, which ruler was used to measure this particular object. In another case, they were presented with a brush like this, and were told that it was 20 units long. So which ruler was used to measure that particular object? We had a lot of activities that required the children integrated the size of the unit, the numerical value, the number of such units, and the magnitude. And again, first they did it using concrete objects where they were able to measure the object with little representations of units. Then they were using gestures, and then they were required to do it in their head. So that is just a very small, brief idea of the intervention activities. The testing that was done before and after the intervention included 2 types of assessments. First, we wanted to see if children actually developed an understanding of measurement unit. And here is just one example of a measurement assessment where they were shown a picture of a ruler and an object that was either aligned or not aligned with the 0 point on the ruler, and they were asked to determine the size of that object. In order to solve this task in the unaligned condition, children have to understand that that the measurement involves iteration of units, not tick marks, not any other algorithmic procedure. The second task illustrated here is an example of numerical magnitude assessment, which is very different from the format in which we instructed children to think about magnitude. So here, it's a so-called triad task. When children are presented with a target number such as 7 and 2 choice numbers, they are asked which of these 2 numbers is closer to the target. So 9 is the correct response here. Half of the items were single-digit items, half of the items were double-digit items. And so let me move to the results. This graph shows the results comparing the performance of the control condition, which is depicted in white bars, and experimental condition, which is black bars. So on the left, you can see that children in both control and experimental condition performed at a very high level with aligned ruler, which simply means that they mastered the procedure. They were shown how to use a ruler. They know how to use it when the object is aligned with a 0 point on the ruler. When it's not aligned, they perform poorly. In fact, they perform below chance because our task was a multiple choice task. They perform below chance because they systematically choose an incorrect response based on their incorrect strategy. So at pre-test, there was no significant difference between the control and experimental group. At the post-test, we see no increase in performance in the control group, but a significant increase in performance in the experimental group. So this clearly should be interpreted as evidence of improved understanding of sort of a mechanism of measurement by children who participated in the experimental condition. These results are for the number distance task, where without any spatial cues provided, children had to decide which number, in terms of magnitude, is closer to the target number. On the left are the results of the control and experimental group on single-digit dyads. And we were somewhat surprised, but these Russian kindergarten children were pretty good at this task. Again, no differences between control and experimental condition here. They both grew at post-test, and the growth was somewhat bigger in the experimental task. But most interestingly, for double-digit dyads, where the level of performance was very low in the beginning, prior to the intervention, we see an increase in performance. You can see that both groups increased their performance, perhaps because it's a time task, and so practice that they had in the pre-test probably helped both groups. But the experimental group clearly increased their performance much more than the control group, so this is the effect beyond just sheer practice. So just one sentence to interpret the results, because I know I ran out of time. The results are supporting this hypothesized link between spatial reasoning and understanding of numerical magnitude, we can see that helping children understand how the unit of measurement works really advances their numerical knowledge. And that potentially we can later think about how this can be brought to the actual classroom beyond the experimental sort of context.
Thank you very much.
Normally teachers have a good enough voice to speak without a microphone, but right now I've had a cold, so I will have to speak into the mic. I would like to share with you my 30 years of experience. Even though by education I'm not a teacher, and it was in a strange way that I became a teacher. Well, many people come into teaching in a strange way. I started teaching at special extra school classes, then at a private school, and since 2003 until today, I've been working at a public school called Intellectual, but that's not an ordinary school. I've been working at this school since 2003, and this is a school for gifted and talented, as is written on its gates. Of course, the programs are different, and the teaching methods are different from the ordinary schools. First, about our program. The program is from grade 1 until grade 11, but here in this presentation I am going to tell you only about the primary school, grades 1 through 4, even though I have been working with elder children as well. So this is what we cover in the first grade: positional systems, arithmetic operations. Then in grade 2 we have negative numbers, functions, graphs, consisting of individual points, and this is enough to do various operations with those graphs, with various movements of planes, to understand the composition and reflection. And in the third grade, I'm having a class of third grade children as well. There's the set theory, the language of math logic, finite arithmetics, these things are covered in the third grade, and these children start to have a proper understanding of integer numbers. And in my understanding, we don't need to hurry things with the fractions. We set fractions aside, we live by the integers, and we have 6 modules in a year. We have 6 modules in our academic year. So one module in grade 1, 2, 3, and 4 is dedicated to geometry. And in the first grade, it's just the general understanding. We cover parallel lines, crossing lines, different polylines. We get acquainted with different things, so we do various problems of combinatorial geometry, how many dots we can put on a line, and how to draw an octagon so that it can be split into 3 triangles, and so on, things like this. In the second grade, we already start serious proving problems, and This is where they cover congruent geometry. They are well acquainted with that. When we are talking about the equality of shapes, we have to prove that certain intervals are equal, certain triangles are equal, and so on. And since the fifth grade, but they are already well prepared for this. Starting from the fifth grade, we start fractions, we start equations with two variables. All the relevant theorems, the polynomials, we started very quickly. I'm only acquainted with the Russian system of education and the American one because I've been living in America for a while and I have worked there. But as far as I know, fractions precede negative numbers everywhere. Why? I don't understand. Because logically, we should first cover integers. Because we do first addition, then multiplication. And it's easier to operate with negative numbers than with fractions. Fractions are quite difficult because there are things like factorizations, 3/4 minus 5/10, understanding that 3/4 and 6/8 is the same fraction. It's not so simple, you know. And in the binary system, it's easier to add numbers. It's easier to understand the mechanism of adding digits, of how a number is structured. It's easier to understand multi-digit numbers. There are a lot of things that we teach that are based on traditions, because a school is a very conservative system. It's not that bad, but we need to understand that this is done by tradition. It's not because it's better, it's because our fathers and grandfathers studied it in the same way. So what are the objectives? Our objectives is to get acquainted with the basic structures and notions, and then we move back by a spiral in the next years. But we need to start with a certain structure. If it's about a language, first it's the grammar, and then it's vocabulary, and then the vocabulary grows. First, we need to understand how a language is built, and then we add up the vocabulary. I thought that's the system. And furthermore, the way towards generalization is becoming easier. I can see that this zone of proximate development is growing very quickly, the same zone which was mentioned by the previous speakers. As for personal development, it accelerates very quickly among children. It's very difficult, you know. I'm the author of this program who has been observing this for decades now. I keep being surprised. I'm a person who can't believe myself in what he sees. And the most important thing here is that it seems to be done under pressure, because of course I am tormenting my children. I never give them the right answers. I never tell them how to solve a problem, and they really want to know how to solve a problem. And very often I finish the lesson without giving them the answer, and they keep thinking about this problem. They can't sleep, and that's good because they develop quickly. They are trying to set it aside, but they can't. They want to know how to solve this problem, and that's a well-known effect. And when you start working from grade 1, many children come to school and they are still curious. They have curiosity. Okay, I understand that I don't have much time. I heard the name of Vasily Davidov here. but we never mentioned his scientific advisor, Professor Galperin. And it is Professor Galperin's theory. I can't talk about it now, I don't have the time. But it is the theory that is the foundation of everything. And we are trying to use all the three types of education, the trial and error type, the second type of education with the algorithms, and then we try using the third type of education when algorithms are built. These are the children. You can see that they can walk around the classroom, they can talk together. Sometimes they are in pairs, sometimes they are in groups. Sometimes people want to work individually, and that's their right. You can see that they have their plastic boards because it's difficult for small children to write on a sheet of paper. And there are also children who complain.
Мы не можем извне, через некоторое время они нас...
And the problem is that very often those children become very advanced, and we can't take even very talented children from the outside, because those children become really advanced. And I would like to thank you for your attention. Thank you.
So, I will give you an insight about a project that we undertake together with a group of information technologists. And this is the group, and we are supported by the German Ministry of Education. The topic is about algebra, learning algebra. And traditionally, tiles and things are used to learn algebra. For example, the upper ones are today also virtual tiles, but they have some kinds of limitations. Haptic tiles lack, for example, feedback, and they don't give hints, and software, they are not haptical for children, and the body is excluded. And what we did is, in our approach, we put together both, and so we developed a hybrid system. And what does the hybrid system do? We want to develop a system that helps the students to learn algebra, and therefore we address conceptual learning in that we model variables, numbers, and expressions by tiles, and actions and operations by actions, as always is done. The question is how, and this is a short insight of our kind of mapping. The symbol system in mathematics is one system, and we try to map all those parts that are important onto our MAL system. MAL is multimodal algebra learning. That's the name of our project. But if we use real tangibles, they also have limitations, so they cannot transport everything. And when learning goes back, that means the other way around. So this one, it does not work really. So it goes from right to left. So when we map with the MAL system from the left to right, and when we learn from right to left, and the learning means it is, with the MAL system, it is reduced like with every didactical system, so that they have to be broadened, this kind of system, to learn everything. And what does the virtual system look like? So this is these are virtual algebra tiles. You see x minus x is red, and ones and minus ones. And then there is a representation of an equation that you can see here. And you can work with that, put on another x tile, and then you get a zero pair in the US. This is quite well known. That vanishes, and then you have another zero pair that vanishes as well. And you can organize all those within grouping in groups, and then you have a relationship between both sides that is kept, which means that the solution is kept the same. And when you use a division gesture, Yeah, and we have designed this gesture within the virtual system, then it is only one short relation left, and the students can learn what division in the use of equations mean. So this is the virtual situation. So yellow means no mistake, red there is a mistake, and green you are ready. So now the hybrid system, it looks like this. You have real tiles on the paper sheet in front of you, and this is mapped onto the display, and the display interprets this in terms of the one we have seen before and gives a kind of feedback through the markers. And so the students can use really material tiles but get feedback virtually. Yeah, well, this is the surrounding of our question. We do some research in it within algebra, and our question we have investigated is which obstacles are left for students after they've learned algebra. A lot of obstacles are there. But we don't really know which ones and what still keep to be the same. And we thought this system is really new, and when students have learned algebra, and those who have understood algebra will very quickly be able to translate it into the new system, and we would really see what kinds of problems are kept after learning algebra. The method to 22 7th graders, 1 week after an exam about algebra, they solved 5 tasks, 15 minutes for all those tasks, and high proficient students were able to solve it within 10 minutes. Well, this is a topic work in progress, and what we found is the main problem is really translating a text or symbolic expression into another representation. And there are 3 main obstacles. The sign is an obstacle. If you think what does minus x mean? The students know in arithmetic what it means, but when you use variables or even terms, it is really difficult to interpret that for them. And important and difficult for them is also an expression of multiplication. So 2x they've interpreted with these tiles in the following way. So this way, in an additive way, that's obviously wrong, and you can really see that. And when you use symbolic expression, you cannot see this. And the third one is a reversal arrow, and I will give you some insight about the reversal arrow. The reversal arrow has been investigated for quite a long time, and Morgan-Sneeze in the last PME has explained why why this reversal arrow is not really understood. It's still a problem that appears everywhere in the world, but we don't really understand how it happens and why. And so we gave the students the following task. Hannah is 1 year younger than her brother, Jan, and he will be 5 next year. So how old is Hannah? It's an easy task, but there are reversal arrows within these tasks. And let's see what the students did. On the left side, you see the translation. So x on the left side is the age of Hannah, and they interpreted x minus 1. Younger than is minus 1. And this is kept all the way through. And the students came from a very high proficient school in Germany, and all of them have started to solve this equation in this way. And on the right side here, you see 3. That's a solution. So that's not a relation and not an equation. So she has interpreted the task in a different way. So the solution is already there, so the equation is not presented here. Here you find the similar, not a similar way, but another problem. On the left side, again, this kind of sequential translation. And on the right side, there is an x-tile. That is Jan, and he is 5 years old, and so they put on 5 units. And what she did was making a story out of the text, translating the text as a specific story. She worked differently on the 2 sides of the equation and did not take the equation as one object. We have another one, so this student has started in the same way and realized on the left side that there was something wrong and added, a 1, because then on the left side it is the age of Hannah. And on the right side, this student put on 5 units, but this is the age next year. And so the relation is not specific concerning the point of time. And that is an insight we had which we did not know before. And this is a similar kind of situation, only that on the right side, the student interpreted the age of Jan today and not next year. So that was a series of pictures of our qualitative analysis and what were the results. So sequential translation of text, it does not work and makes problems. And the students, all of the students start with this kind of translation, all of them, and they are high achieving. So, and that goes together with another problem, that the students take the text as a story. And this sequential interpretation aligns with seeing the task as a story. And this story was represented in many tasks. And then they interpreted one side as Hannah, the story of Hannah, and the right side is the story of Jan, or vice versa. The next problem is the relationship, the relational interpretation of the whole situation. And here the relations have 2 points in time, today and next year. And the students have to make a choice and to keep the relation the same. And that's really difficult for them. And finally, the students often work separately on both sides. On the left side, they try to make sense of the text on the left side of the equation, and then on the right side, they have to consider the equation as one whole thing. And that's obviously a very difficult kind of work. So what do we have to do in future? We have to vary the task, because that was only one task, and to get an overview how this kind of reversal error, so reversal error means that the text has to be interpreted in a reversal way. No, not the age of Hannah -1, but the age of Hannah +1. That's the reverse interpretation, which is so difficult. And in this sense, in this task, we have a number of additional difficulties which appear in all those kinds of tasks. So thank you for listening. And that was it. I hope I did not exceed the time.
You're great. Time management. Now, just, take some seconds to remember all 3 speakers, because now we're going to discuss all the 3 presentations. I would ask all the 3 of you to come up here, so people are going to ask you. Feel yourself comfortable.
So I have a headset. I can keep.
I will take advantage of me being a chair, so I want just to ask Angelika a small question on your presentation. What age were your students?
Oh, sorry. Age, it was 7th graders. 7th graders, it's about 12 years old.
Oh, great. Thank you. So, have you thought of some questions? I think we'll do it in a classroom, raising your hand.
Yeah.
And about language speaking, I guess that will be fair to ask Angelika only in English.
Yeah.
So try your best, and we can ask in Russian both Marina and Yakov, or in English, and I hope we'll have some translation. I will help in case it is needed. Okay, so you start, please.
Thank you, all of you. It was very wonderful 3 presentations. And my first question is for you, Marina. In the activities you did with your young students, how we can describe the role of the language, especially what attention did you pay to how students speak, and at what moment how students explain? Does they speak? And do you ask them to speak? And so what was the role of the language and students' language? You can answer any language, at least for me.
Once again,
I can explain.
okay if Marina answers in Russian.
Yeah.
Окей, хорошо. Мы
We didn't pay that much attention to the wording of the children. It was mainly about gestures and about using the material. At the same time, we had some moments when children needed the repetition of something, then they took part in the discussion. They had discussion between themselves about how to do it, because they had those activities when children were doing something, measuring something, and they had to prove to the class that their measurement was right. So we were including the explanations coming from a child. Well, it was one of the pedagogical approaches, so to say, but mainly it had to be decided by the instructor to which extent to rely on them. Our guidelines were, our instructions were mainly about how to use the material and how to use the gestures. And then from time to time, children heard. And now you have to imagine this in your head, whatever was happening in their head. Here, the main idea was to focus on spatial cues.
Из этого мы исходили, когда эти activities.
And that was the basis for us when we were designing those activities. Well, I'll ask my question in Russian. You can hear the translation, right? Okay. Thank you very much, Marina. Thank you very much. And I have a question to you. Taking into account that you had a short a number of participants, do I understand it correctly that it was mainly qualitative, and you were not controlling such things like family input? Like, so to put it in a nutshell, did you involve the families? No, we were not involving families into our research. Of course, it would have been interesting to collect some information on families or conduct similar research at home and in a class, but we didn't have a resource for that. I cannot call it a qualitative kind of research, because normally when you talk about qualitative research, you think of certain methodology. No, it was a typical qualitative research with a small collection of subjects. But this was an experimental research, and part of the method is random assignment to groups.
Случайным образом дети оказываются либо в экспериментальном.
So it was a random allocation of children to an experimental or to a control group. And normally this process has to compensate for the lack of control. But take into account that, of course, given that we had a small number of subjects, we cannot rely on that. But this kind of research involves certain tension between the necessity to strictly control everything and some major intervention, which is difficult to do with a big number of people. And of course, you have to balance somehow between all that and the desire to expand the number of subjects. I'll ask my question in Russian. I have a question to Yakov. I really liked what you offer to small children, because I agree that when they know how to work with one set and how new it explains them how new elements appear. It's very beautiful done, and you do different systems of calculation, so to say. So my question is, did you check how good are they in algebra later on? Have you checked their students? Yes, I stayed with them till the 11th grade. So what did you observe? Were they able to how did it affect the operations? Well, what can you tell us about that? Well, it depends on what you call algebra. Linear equations with integers, and well, it's third graders that they do them, and they are not concerned much about these operation with brackets. So basically, algebra has started for them a while ago. There is no unexpected transition. The same. They know this disjunction conjunction between P and Q, for instance, different signs. They are used to all these signs and symbols and so on. They don't have some unexpected transition. Well, symbols comes into their life very naturally. Yes, the symbols are already there. Moreover, I want to say that it's easier to introduce that in early age, because they don't have this rigid border between real life and fairy tales. This is the rule of the game. We are working with some letters using certain rules. Okay, I understand that. The next question. How easy it is to translate, like to share this approach? Great question. And I think this question deserves a long answer. Why? The biggest problem here is as follows, something that we haven't covered. As one great teacher said, back then he didn't know me, we met later on. He said he was warning about some dangers. Mathematics is a dangerous thing, he was saying, and he was absolutely right. What he meant was it can be harmful to psyche, such fast development. But here I'm using my experience. I try to feel this border. When I pass this approach on to others, of course I cannot control that. Yes. Yeah, there are some certain followers, and in some family centers in Moscow and some family clubs, not in schools but in clubs, different people use that. Some are doing better, some are doing worse. Yes, I'm trying. Now I have an issue of passing this methodology on, and it's tricky. Of course, it contradicts the natural reactions of the teachers, because the natural reaction when person doesn't understand something, the natural reaction is to explain, but here you have to abstain from it. You have to kind of hold yourself, and it's difficult. Parents very often cannot keep themselves. They try to help and hint, but here you have to pause, and here you have to kind of torture. Of course, when you feel that it's time to keep this interest, you have to hint. But this is a very exhausting thing. It's a sensitive matter. If I may, I want to continue with this conversation with you.
So you're following the curriculum so fast. But what do you do in their final years of school? Well, I have 8th and 9th graders. For instance, in 8th grade now, we are working on complex numbers. We do the topology in 9th grade now. And how do they allow you to deviate from the curriculum, from the state standards? Well, I'm not asking them. I'm not asking for permission. Thank you. I was protecting Angelica with my body for her not to escape from us. So maybe we'll have a question to her. I'll ask the following question. So, I didn't catch it. How do you move on to schemes and to operation with letters, or you were interested in activities with subjects? No, but I mean the cards. I mean the cards. There were activities with an object, and then there were certain schemes and then letters, or it wasn't a concern for you, and you were just following how objects help. I mean the objects. I mean the objects you were using.
Yes, now it works. So, so our yeah, good, thanks. Our research is about developing this tool, this hybrid system, to include both, on the one hand, the materials, and then on the other hand, the virtual system. And this, well, the transition to symbolic representation does not appear by itself. So this has to be done by reflecting, and the teacher is not excluded. So it's just a way to help the teacher to save time for specific difficulties, because this system gives feedback, and so the teacher does not always have to go to the single students and say, that's right, that's wrong, you are on your good way. So all this is done by the system, but when the students have really difficulties, the teacher has time to go on with them. And the transition to symbolic representation is really an important one, that's clear. And well, we are not ready, so we are developing this tool. And I think, as others also have experienced in research, so this only can be done by reflecting on what they've done. So there has to be a reflecting phase where the students look at their own actions, what they did, and how these actions lead to the results. And so the teacher is definitely needed, and the zone of proximal development is also there in class once this is implemented into the classes. So.
May I also make a comment on the 3 of your presentations? Because, well, we have heard 3 of them, and well, we can say that in all your presentations, a special action of children was in the center. Yeah. We can say that in your presentation, it's measurement, it's a classical action, a classical Davidov's action. But in your report, I would say that your action, the thing that children tried to do, really what they did, was to translate the text of the problem into pieces of objects in front and in things on the screen. It was, well, the main action was the translation and then trying to illustrate what they got from the problem. What would you say about that?
Well, I think the translation is one thing, and we investigated the kind of errors that they make, the students make.
You know, we don't exactly can figure out what means investigation in terms of a child's actions.
Yeah.
He was reading the text, and he was trying to bring down each word of the text
Yes, that's
into
one
something.
Yeah.
And was there another action?
Yes, there are other actions. The actions that's a system model. So these operations with the variables, and so these are translated into acting with the kind of variables and things, so that they develop a sense of equivalence relation and equivalence transformation. So these are the mathematically informed
kids were always
actions.
going between
Yes.
things here and the text, and trying to do the equation and go back and
Yeah,
then-
that's also, that's a
fine.
translation, but also
Well-
within a system there are also actions. So the students take variables away. So that means it is subtracting. They put them on. The division gester is dividing a equation by a number. And so you have a different number of equivalent relation that is induced into the system so that students can get a sense of what it means, for example, to divide an equation by 2, by 3, or by something else. And we have investigated where there is research about it. We didn't find anything. So there is nothing about how a student can learn and build an image of what does it mean to divide a real equation by a number.
then
So it's only symbolic and calculating things.
Well, okay, and at last, I guess your presentation, and you said this word was learning to play by the rules. Они играли по правилам, то есть они, вот это вот их освоение алгебры, то есть они принимают эти правила.
That means that they learn by the rule, they accept those rules, and learn how to use them. That's what the children do in the primary school.
So invent rules. Okay.
Well,
Извините.
Yakov also
no,
yes,
right.
said that they also invent rules, not only play by them, but invent some new rules. Well, can I make a comment for every speaker, if we have time? Well, I would suggest for you to take into account not only measuring action, but also counting, which is a special separate action. And yes, we can find that these traces in David, because if we are talking about number line, the action of measuring is not enough for it. So we can also add some special things for the program if we want to develop understanding of number line. And there is a special mistake with children when they mix the ruler and the number line. Also interesting things about that, for example, in 91 school, about yes, you know, I know you have to go, but still, I strongly advise you to read about how it is this problem solving is done in Davidov's works, as were in Russia, plus. Because, well, what I think colleagues were asking about is about the model that mediates children solving the problem. Like, how do they solve it? Not how do they illustrate it, but how do they really solve the problem? Well, perhaps we can talk about that later.
Yes, but there is other works around, so I think you've studied it. But
Okay. So, any other
we have to
questions?
go.
But yes, we have run out of time. But well, it's really exactly 1 hour after we started. So I guess we can continue in the break.